Today we're at a facility they don't exactly advertise, but one the modern world can't live without. I'm standing in front of a massive complex where they produce TNT, that explosive material that blasts through rocks and quarries, sends rockets into the sky, and, when necessary, strikes back at the enemy. Everything here smells like chemicals, metal, and that industrial power that sends shivers down your spine. The territory stretches hundreds of yards in every direction. Concrete walls, pipes, tanks, and above it all, a low but constant hum of reactors. Let's walk through together. I just got my access pass, and we're heading into the production floor. Hold on tight, it's gonna get intense. TNT, or Trinitrotoluene, showed up back in the 19th century when chemists started experimenting with toluene, a colorless liquid you get from coal or petroleum. 166 years ago, a German chemist named Julius Wilbrand heated toluene with a mix of acids and got a yellow crystal that detonates with monstrous force. Since then, TNT became the king of explosives, stable, powerful, won't blow up from impact or fire, only from a detonator. You can drop it, heat it, shoot it with a rifle, and nothing happens until a blasting cap goes off. That predictability is what made it indispensable. 1 gram of TNT, that's the benchmark unit for measuring explosive force, the standard all other substances get compared to. Here at the plant, everything starts with massive tanks of toluene. This liquid flows into reactors, giant vessels made of stainless chromium molybdenum steel, because regular steel gets eaten away by acids in a matter of weeks. They pump in a mixture of nitric and sulfuric acids, concentrates that'll melt right through gloves. The reactor temperature is kept around 195 to 212 degrees Fahrenheit. Hot enough to keep the reaction going, but not so hot that it spins out of control. The nitration process happens in stages, taking anywhere from several hours to several days. First, you get mononitrotoluene, then dinitrotoluene, and finally trinitrotoluene, TNT itself. At each stage, another nitro group latches onto the toluene molecule, and with every step, the stuff gets more and more explosive. The acids circulate in a closed loop because they're regenerated and reused, not just dumped into the ground. Operators in protective gear monitor the gauges, pressure, temperature, concentration. Everything stays locked down because the slightest slip and the reaction could go sideways. From the reactor, the mixture flows into coolers, long coiled tubes where the hot TNT crystallizes. Then it's into settling tanks. The heavy TNT sinks to the bottom while the lighter acids get skimmed off. What you're left with is a jelly-like mass, crude TNT, still damp with acid. It gets washed with hot water at around 160 to 175 degrees Fahrenheit to neutralize what's left. The water changes 3 times. The first run comes out yellow with acid, the second is cloudy, and the third is clean as a tear. The spent water doesn't just get dumped. It's neutralized with lime and holding pools, filtered through a sand layer about 10 feet thick, and only then sent to treatment facilities. Ecology stays under control because acid is poison to anything living. Meanwhile, the crystals get unloaded. The mass is already solid, but still 6 to 10% damp. Now comes drying, one of the most fascinating stages. The vacuum drying chamber, a room where rotor drums hum, each about 6.5 feet in diameter. TNT gets loaded in batches of 200 pounds. They seal the drum, pump the air down to a pressure around 4 inches of mercury, and fire up the heat to 130 to 140 Fahrenheit. Fans push warm air around inside. The drum rotates, crystals tumble, dry evenly, no sticking to the walls. 2 hours, and out comes pure yellow powder at 0.5% moisture. Skip this step, and TNT would clump together or go unstable from the dampness. powder color ranges from light yellow to deep orange, depending on purity. Here, they're producing top-grade stuff, 98% pure. Next up, granulation. They moisten the powder, press it into matchbox-sized bricks under about 3,000 pounds per square inch. These bricks come out hard as rock. Then they crush them in hammer mills, where shafts spin at 6,000 revolutions per minute, turning the bricks into granules between 1 and 3 millimeters in diameter. Why granules? Because they're easier to pack, don't create dust, and detonate uniformly. The dust gets sucked out by ventilation because breathing in TNT is bad news. The granules get poured into sealed crates holding 100 pounds each. That's the standard for quarries and the military. Every crate gets checked for moisture, no more than 0.7%. Otherwise, the TNT starts to sweat and becomes sensitive. There are special molds for underwater charges too. The pellets get mixed with paraffin so they don't get wet. The crates are sealed, labeled by batch, and sent to storage. From here, the TNT heads out to quarries, mines, military bases. One crate is enough to blast through 200 tons of rock. Now, about safety, because without it, they wouldn't last a day here. The plant is divided into zones. Reactors sit inside concrete shelters at safe distances from each other, with anti-detonation barriers between them, about 50 feet high, made of reinforced concrete. The logic is simple. If one reactor blows, the barrier absorbs the shock wave and keeps the detonation from jumping to the next one. No open flames, no sparks. They even hand over their cell phones at the entrance. All electrical equipment is explosion-proof, lights sealed in airtight housings. Personnel wear anti-static clothing, shoes with conductive soles so static doesn't throw a spark. Every 5 minutes, sensor checks for gas leaks. Emergency showers and CO2 fire extinguishers everywhere. Were there incidents? In the 19th century, explosions wiped out entire factories, but now, 0 accidents in the last 10 years. Why? Because of automation. Computers shut down the reactor in seconds at the slightest anomaly. One operator at a console monitors 10 processes simultaneously. Compare that to the old factories. Back then, everything was done by hand. TNT was packed with bare hands. Explosions happened regularly. Now, robotic manipulators, sensors, cameras. Evolution. Let's look inside the lab. This is where they test every batch. A sample gets placed in a bomb chamber, a thick-walled steel cylinder. They detonate a milligram and measure the detonation velocity, around 22,600 feet per second. If the velocity is below spec, that means there are impurities in the batch, or the crystal structure is compromised. Then they check stability. Heat it to 200 degrees Fahrenheit, drop it from 10 feet, it shouldn't crack or detonate. Then there's friction sensitivity. The cylinder spins for 6 hours, and if it doesn't blow, you're good. Lab techs check purity with a chromatograph. Toluene or acid traces, not allowed. Production here is massive, 1,000 tons per month. Power comes from their own gas turbines and steam boilers. Waste? They regenerate the acids, redistill the toluene, send it back into the cycle. Filters on smokestacks 200 feet tall. Wastewater cleaned until it's crystal clear. Nearest town is 10 miles out, so no complaints from the neighbors. Interesting fact, TNT isn't just for blowing things up. Melt it at 180 degrees Fahrenheit, it turns liquid like hot wax, and pour it into shell casings. Or mix it with other compounds for plastic charges. In quarries, 1 ton shatters a boulder the size of a 3-story house. In mining, you can't drill a mile-long tunnel without it. In the military, it's the backbone of torpedoes, mines, and aerial bombs. I'm standing in the granulation shop right now. hearing the press rumbling, watching granules pour into bins like golden sand. The air's clean, but there's that distinct chemical smell, a familiar scent to anyone who's been inside plants like this. Discipline here is ironclad. 8-hour shifts, every action by the book, every step under camera. The people here are like jewelers, except they're not working with gold. They're working with explosives. The factory's like a living organism, roaring, spinning, producing power. TNT isn't evil. It's a tool. It builds roads, digs mines, defends the nation. Without it, there'd be no 1,000-foot bridges, no tunnels carved through mountain ranges. From the yellow crystal discovered a century and a half ago to today's high-precision production with robots and computers, it's been a massive journey. But the essence remains the same, turning chemistry into controlled force. There's a metal so rare that humanity mines less of it in an entire year than it does gold in a single day. A metal that costs anywhere from $4,000 to $9,000 per kilogram. A metal you've probably never heard of, yet right now it's keeping the plane you flew on for vacation from falling out of the sky. This is rhenium, the rarest stable element in Earth's crust. A silvery white metal that doesn't exist as a standalone ore and is only extracted as a byproduct. Without it, there would be no modern jet engines, and aviation would be stuck at mid-20th century levels. Let's start with the scale of rarity. Rhenium makes up about 7/1,000ths of a part per million in the Earth's crust. For comparison, gold is 4/1,000ths, platinum is 5/1,000ths. The numbers seem comparable, but there's a fundamental difference. Gold and platinum can be found as nuggets or concentrated ores. Nature sometimes gathers them in one place. Rhenium is never found that way. It's scattered as microscopic impurities in other ores, mainly molybdenum and copper. The concentration is so low that even calling it rhenium ore is incorrect. It's always ore of something else that happens to contain rhenium. Rhenium itself looks like a silvery white metal with a slight grayish tint. But most people have never seen pure rhenium. Even in industry, it's more often used as alloys or powder. In nature, rhenium occurs in just one mineral, jacasganite, which is so rare it literally exists in only a few places on the planet and has no industrial significance. All industrial rhenium comes as a byproduct of processing molybdenum concentrates, which themselves are a byproduct of copper mining. A byproduct of a byproduct. That's what rhenium is. Think about the scale here. To get just 1 kilogram of rhenium, you need to process roughly 200,000 tons of copper ore. 200,000 tons of rock for a single kilogram of metal. It's like searching for a needle, not in a haystack, but in an entire field planted with hay. The main sources of rhenium are molybdenum mines in Chile, the US, Kazakhstan, and Armenia. Chile dominates, about 50% of global production. The Chuquicamata mine in the Atacama Desert is one of the largest open-pit mines on the planet, where they extract copper and molybdenum, pulling out rhenium along the way. The pit is so massive you can see it from space, roughly 2 3/4 miles long, nearly 2 miles wide, and over 3,000 feet deep. Extracting rhenium is complex and multi-staged. First, copper ore gets mined and enriched through flotation to produce copper concentrate. That concentrate contains molybdenum, which also gets enriched and separated out. Molybdenum concentrate is molybdenum sulfide with microscopic traces of rhenium, typically 0.05 to 0.2%. Sounds convoluted, but it's essentially a chain. Copper ore to molybdenum concentrate to rhenium solution. At each stage, volume drops by factors of thousands, while value skyrockets. The molybdenum concentrate gets roasted in special furnaces at around 1,100 degrees Fahrenheit and higher in open air. Molybdenum oxidizes to trioxide, which can then be reduced back to metal. But rhenium behaves differently. It oxidizes to rhenium heptoxide, which vaporizes at this temperature and escapes with the gases. Those gases pass through a complex system of scrubbers, towers where they're washed with water or alkaline solutions. Rhenium heptoxide dissolves, forming rhenic acid or paranates. Rhenium concentration in these solutions is tiny, grams per liter, but that's something you can work with. The solution is purified of molybdenum, copper, lead, and other metal impurities through multi-stage chemical treatment, extraction, ion exchange, precipitation. Then rhenium is precipitated as a white crystalline powder, ammonium perrhenate. This is the most common form of rhenium feedstock for further processing. To obtain metallic rhenium, the powder is heated in a stream of hydrogen at temperatures exceeding 1,800 degrees Fahrenheit. Hydrogen reduces the rhenium oxide to pure metal. The result is rhenium powder, which can then be sintered, melted, or used directly in alloy production. Each year, humanity produces about 50 tons of rhenium. 50 tons! That's the entire global output. For comparison, about 3,000 tons of gold are mined annually. Copper, 20 million tons. Rhenium is so rare that global reserves at any given moment are measured in hundreds of tons, not thousands or millions. Here's the question: why mine something this rare in the first place? The answer? Jet engines. About 80% of all rhenium goes to the aviation industry for making superalloys that form turbine blades. A jet engine turbine blade operates in absolute hell. Gas temperatures hit 2,700 degrees Fahrenheit. That's above the melting point of the alloy the blade is made from. So it's cooled from the inside by airflow through microchannels. The pressure is colossal. The blade spins at tens of thousands of revolutions per minute, experiencing monstrous centrifugal loads. A corrosive environment with sulfur impurities from jet fuel. And all of this for years of continuous operation with zero margin for error. Because if a blade cracks mid-flight, the engine destroys itself. Nickel-based superalloys, the primary material for blades, contain nickel, chromium, cobalt, tungsten, molybdenum, aluminum, titanium. But even these incredibly complex alloys couldn't withstand high temperatures for extended periods, until they added rhenium. Rhenium does something remarkable. It dissolves into the nickel matrix of a superalloy and blocks defect movement in the crystal structure at high temperatures. This is called creep, the gradual deformation of metal under load when heated. All metals creep, but rhenium slows this process down dramatically. Adding just 3% rhenium to a nickel superalloy raises the operating temperature by about 54 degrees Fahrenheit. Doesn't sound like much? But in jet engines, every 18 degrees of additional temperature yields roughly 1% more efficiency. And efficiency means fuel consumption, flight range, airline economics. Modern superalloys contain up to 6% rhenium. A single turbine blade can hold anywhere from 5 to 20 grams of rhenium. One engine on a large passenger jet, about 13 pounds of rhenium in the blades alone. 13 pounds of metal worth up to $50,000 in a single engine. And a plane has 2 engines. Every year, thousands of jet engines are manufactured. Passenger, cargo, military, and virtually all the rhenium mined goes straight into them. Because of its rarity and high cost, the industry is desperately trying to reduce rhenium consumption. New generations of superalloys with lower content are being developed, along with the use of ruthenium, an element from the same group that could theoretically replace rhenium. But ruthenium is even rarer and more expensive, so for now, it's just research. Single crystal blade technology makes rhenium work smarter. Instead of a regular polycrystalline structure, each blade is grown as one massive crystal with no grain boundaries, which are weak spots at high temperatures. This lets you cut down on rhenium content while keeping performance. But the process is complex and expensive. Each blade is grown individually in specialized vacuum furnaces with extremely slow, controlled cooling that takes hours. Recycling rhenium from spent blades is mission critical. After thousands of hours in hellish conditions, blades wear out and get replaced. The old ones don't get tossed, they're melted down, rhenium and other precious metals extracted, and used again. Around 30% of rhenium comes from recycling, more than most other metals. And the reason's simple. At these prices, nobody can afford to throw rhenium away. The remaining 20% of rhenium is used in other areas. Platinum rhenium catalysts in oil refining to boost gasoline octane ratings, filaments for mass spectrometers and electron microscopes, anode materials for X-ray tubes. The strategic importance of rhenium is enormous. Countries without access to rhenium cannot produce modern jet engines. And this isn't just a matter of civil aviation, but military, fighters, bombers, cruise missiles. Interestingly, rhenium was one of the last stable elements to be discovered. German chemists found it in 1925 while examining platinum ore through spectral analysis. They named it after the Rhine. Before that, Mendeleev had predicted the existence of element number 75, but no one could find it because of its extreme rarity. Basically, the entire world supply of this metal would fit in a few trucks, and the whole world's aviation depends on those few trucks. Hey everyone, on this channel we go behind the scenes where cameras usually aren't allowed. If you're into this kind of breakdown, hit subscribe and tap that bell so you don't miss new episodes. Every year, the world recycles over 1.5 billion tons of scrap metal, and hidden within this chaos of rust and mangled iron is something way more valuable than it looks. What seems like trash today could save your life tomorrow at 75 miles per hour. But how exactly does this pile of metal transform into a precision-engineered component trusted by millions of drivers? And why can even a tiny 1% error destroy an entire batch? There's one detail in this process almost nobody talks about, and it's what determines whether your car stops when it really matters. Today, we're breaking down the entire production of brake rotors, from the furnace to final inspection. It all starts with what most people would just call a junkyard. And that's pretty ironic. What will later stop your car at 75 miles per hour, right now looks like a giant pile of rusty junk. Old cast iron radiators, car body fragments, twisted beams, and other metal scrap. It's all stacked in heaps on the lot outside the plant, and rain sends rusty orange streaks running down into the asphalt. But to this factory, it's all treasure. A massive electromagnet hanging from a crane scoops up several tons of this iron and drops it with a crash into the throat of a giant induction furnace. Induction, meaning the metal doesn't melt from fire, but from an electromagnetic field that heats it from the inside out, evenly and fast. If you stand too close, it's kind of terrifying. The furnace hums at such a low frequency that you don't really hear the sound. You feel it deep in your chest, like your heart's trying to sync up with this heavy industrial rhythm. The temperature inside the furnace climbs to 2,700 degrees Fahrenheit. At that kind of heat, even the toughest steel turns into liquid. More like glowing, ridiculously dangerous soup than anything solid or dependable. When the furnace tilts to pour out the molten metal, everything around you floods with bright orange light that makes you want to squint. No artificial beauty here, just brutal physics and an insane amount of heat. Every batch of metal gets tested instantly. Lab techs in special suits grab a small sample, cool it down, and within seconds determine its chemical makeup using a spectrometer. The device breaks the sample down into elements and spits out precise percentages of each component. If the carbon or silicon content deviates from spec by even 1%, the entire massive batch gets sent back for remelting without hesitation. Mistakes aren't tolerated here, because the cost of that kind of error to the end user could be way too high. Next, they pour this liquid fire into molds. They use sand casting technology here. Sand seems like an unreliable material, but at this factory, they mix it with special resins and under enormous pressure, it becomes hard as concrete. The molds are made with jeweler-like precision. The internal relief copies every detail of the future disc, including cooling fins and mounting holes. Metal fills the cavities inside the sand mold, and it's at this exact moment that the rough blank of the future brake disc is born. It doesn't look anything like that shiny part we're used to seeing in auto parts stores yet. Instead, it's something big, heavy, and really dirty. After pouring, the discs need to cool naturally. It's a long process, sometimes taking several hours, and this is critically important. If you try to speed up the cooling, say by splashing water on it, the metal becomes too brittle. A disc like that could just shatter into pieces at the first hard stomp on the brake pedal somewhere out on the highway in the rain. When the blanks cool down to just warm instead of glowing red hot, they head to the machining shop. This is where robot territory begins. They work 24/7, no lunch breaks, no complaints about tough working conditions. Each disc gets grabbed by a manipulator arm that loads it into a CNC machine. Special cutting tools shave off excess metal as easily as if it weren't solid cast iron, but a stick of cold butter. Chips spiral out red hot and drop into a collection tray while a smooth, precisely calibrated surface emerges from under the cutter. At this stage, fanatical precision rules. A deviation of 0.8 of a millimeter means hopeless scrap. A disc like that never makes it to the warehouse because it'll cause vibration that'll just destroy a car's suspension in a few months and force the driver to shell out a ton of cash for repairs. The machine finishes one disc in several minutes, and each one comes out identical to the last. Robots don't get tired and don't lose focus by end of shift. It's fascinating to watch as the perfect, almost mirror-like surface gradually emerges from a rough and ugly form. Then they drill ventilation holes and internal channels into the discs. This isn't done for visual style like some people think. It's a critically necessary cooling system, without which the disc simply wouldn't survive serious loads. During heavy braking, the disc can heat up to 1,300 degrees Fahrenheit. At that temperature, it glows dark cherry red. If this heat isn't removed in time, the metal starts losing its friction properties, and the brakes just disappear at exactly the wrong moment. So these holes and channels, they're the result of extensive engineering calculations, not some design decision for looks. Each channel has a precisely determined diameter and angle, calculated so airflow pulls heat away from the working surface as efficiently as possible. Once all the excess shavings are removed, each rotor gets sent to dynamic balancing. It's a lot like what they do to your wheels at the tire shop, but the precision here is tens of times higher. A special device spins the rotor up to enormous speed and uses sensors to detect the slightest weight imbalance. At these rotational speeds, any imbalance turns into noticeable vibration, and the machine picks it up with gram-level accuracy. If one side turns out to be heavier by even 3 or 4 grams, the machine automatically drills out a tiny, nearly invisible dimple in just the right spot on the face to even out the weight. After that, the rotor is perfectly balanced and ready to perform at any RPM without any extra noise or judder. It's at this stage that the difference is made, whether the driver will feel every imperfection through the pedal or whether braking will stay smooth and silent at any speed. I asked the chief engineer how many of these rotors they produce in a single full workday. He just smiled wearily and said they stopped counting them individually a long time ago. They track output in thousands of tons of finished product per month. Just think about that for a second. This facility supplies parts for nearly half the European automotive market, which means every other car you see on city streets is probably stopping with rotors made right here, in this loud, scorching hot plant. Before packaging, the rotors go through a protective coating process. They're either painted with a special heat-resistant paint or coated with a thin, anti-corrosion, zinc-based layer. The coating gets applied in a chamber, the rotor hangs from a conveyor, and automatic sprayers evenly cover it from all sides. This is done so they don't turn into a rusty chunk of metal during long-term warehouse storage or while crossing the ocean in a shipping container. Sure, after the first few miles of driving, this paint on the working surface will completely wear off under the massive friction from the brake pads, but the edges and internal parts will stay protected from road salt and grime. The final, and arguably most critical stage, is the quality control check. And we're not talking about some tired worker giving it a quick once-over at the end of their shift. They use ultrasonic scanners and X-ray machines. They're hunting for internal defects, air bubbles or micro cracks you couldn't spot even with a magnifying glass. Ultrasound sends a wave through the metal, and if there's a void inside, the signal bounces back distorted. The machine flags the problem zone instantly. Even if the disc looks flawless on the outside, but the X-ray reveals a cavity just 2 millimeters wide somewhere deep in the metal, it gets sent straight to the shredder. Nobody cuts corners on safety here, because everyone knows full well, this part directly determines whether the driver and passengers live or die.